Well, thank you for the introduction. Yeah, I'm at the end of my second year of my PhD with Sarah Waters and Derek Moulton at Oxford, and I'm working on modeling tendons, particularly tendon damage, and we're using a poroelastic framework. So first of all, what are tendons? They're the tissues that connect our muscles to our bones. So here we've got a diagram of the Achilles tendon, which is connecting the soleus muscle in the calf to the calcaneus bone in the heel. And they play a really important role in withstanding large tensile loads, which sometimes fails and can lead to a very common and painful condition called tendinopathy. You might be more familiar with the initial inflammatory stage, which is called tendonitis, but that can degenerate into disease. And it's classified as an overuse injury or disease. And from various experiments and imaging of the diseased tendon, we know that it exhibits a different tissue structure, an altered composition and volume. But there's a lot that we still don't understand about how these changes come about and how it really affects the mechanical function of the tendon. So the sort of broad aim of my thesis is to build a model to understand the effect of tendinopathy on the mechanical function of the tendon. Okay, how do we build a model for tendons? So tendons are about 50 to 70% water. It depends on the type of tendon. And then they have this collagen-heavy solid matrix. This is a diagram of the collagen hierarchy within tendon. So you have these highly aligned fibers, and then there's some other non-collagenous components, a few cells sort of hanging around. And then we also know from lots and lots of experiments that all sort of agree on this qualitative curve for the stress-strain relationship, that it has this nonlinear relationship with particularly the sort of toe heel region at the start, and then it goes linear. And they can undergo quite large deformation. So sort of from these elements, a popular model to use for tendons has been poroelasticity. And in particular, we want to take this to nonlinear poroelasticity because of this nonlinear stress strain curve that we're seeing, and the possibility for large deformation. So because we are in a gel seminar, I assume you probably already know what a poroelastic material is, but just to briefly introduce it, you've got lots of solid grains which form a solid skeleton, and then this solid skeleton, you've got fluid that fills the pores of this solid skeleton. So you can imagine a sponge, which can represent your dry solid skeleton, and then if you put it in a bath of fluid, then the fluid is going to fill the pores, and then you get this poroelastic material. And very often we consider the solid grains to be incompressible, which is our case, but then the solid skeleton as a whole is going to be compressible through pore rearrangement. Okay, and so we're going to take this and apply it to our tendon. So we're going to take our tendon and assume that it deforms uniaxially in the z-axis. This really simplifies the system because we can write equations down in one dimension, and it makes it easier to solve and analyze, but of course it is a simplification. So here I've got the z equals 0 boundary at the muscle and the z equals 1 boundary at the bone. And I'm going to write down the poroelastic governing equations in Lagrangian variables. I'll come back to why in a bit. So here capital phi is the Lagrangian porosity, which is the current volume, fluid volume fraction with respect to the initial frame, and phi naught is the initial porosity. This equation comes from conservation of mass of the fluid phase and the solid phase. And then this part of the equation comes from assuming Darcy flow for our fluid, where K is the permeability, which, as you can see here, depends on the porosity. We can do that because we're in a nonlinear framework. And then P is the fluid pressure. And here, this is mechanical equilibrium, where S prime is the effective stress, and we take the effective stress because in a poroelastic material, the fluid is always exerting a pressure P on the solid skeleton, even when the fluid is at rest, and so that cannot contribute to the deformation. So we need to consider the effective stress if we're considering deformation of the solid. As for our permeability law, we're going to just use the Kozeny-Kármán permeability law, which of course isn't particularly for tendons, but it means that permeability increases with porosity, which is somewhat in agreement with the literature. As for the boundary conditions at the bone, we're imposing no flux, and we're going to assume that it's impermeable there, and there's no displacement. That's because the bone is a lot stiffer and a lot denser than the tendon. And then at the muscle is similar stiffness to the tendon, so we're going to assume that there's free flow there, and the muscle is applying a cyclic stress or a cyclic displacement. We'll look at those two boundary conditions, and so it's going to be a tensile cyclic stress. So it's going to be pulling on the tendon cyclically to mimic the sort of daily activity that you might be subjecting your tendon to. Right, I haven't said anything about the stress law yet, or how we're introducing damage. So one simple way that we can think of modeling damage in this model is by introducing heterogeneity, material heterogeneity. And so one way that we can do this is introduce a heterogeneous stiffness. So the stiffness will come into our stress law. So if we take a simple elastic stress law here, so neo-Hookean elasticity, a simple nonlinear stress law, which I've written down here. The details aren't particularly important. This is just what it looks like for our 1D poroelastic model. But M and lambda are stiffness parameters here. And we're just going to locally decrease the stiffness with this inverted Gaussian. And so that's going to be characterized by damage location L. So I'm locally decreasing the stiffness at a location L by a damage magnitude D. And so L and D are two parameters that we can vary and see how that affects the poroelastic response. Okay, that's pretty much our system set up. So now I'm going to show you a few simulations, what happens when we have this heterogeneous stiffness. So here we're going to look at an applied stress with this combination of parameters, which is sort of vaguely motivated by tendons. And then we're going to be looking at the strain or the porosity response. So in this 1D uniaxial framework, the strain is equal to the normalized porosity, so the two are equivalent when we're interpreting them. So you can sort of choose to interpret these as you like. So I'm going to show you first what it looks like in the homogeneous case, where there's no damage. So the muscle is pulling on the tendon at that boundary, and so the strain increases there. That's the boundary condition, and then that response is diffusing down towards the bone, so from z = 0 to z = 1. So the system is diffusive, and that's you can see that from the equations. It's a nonlinear diffusion equation. And so on average, the strain is going to be greater at the muscle and smaller towards the bone. That depends on the point in the cycle, of course, and it also depends on the frequency, because the way it's going to diffuse depends on the time that it takes to diffuse through the material depends on the poroelastic time scale. And so that's tied to the frequency. So these are all non-dimensional parameters here. Okay, now let's see what happens if we have heterogeneous stiffness at L = 0.25, so relatively close to the muscle. And we're seeing this increase in the strain about that damage point. And then similarly, if we move the location of that damage, then we also get this increase in strain about the new damage point. So in both cases, we're getting an increase in strain about the weaker point, which makes sense because we've weakened our material there and we're still applying that same stress. So it's going to get strained more. Now, we've just sort of characterized this by looking at some simulations. It's time dependent, but really what we like to do is have more of a static figure that can sum this up. So to do that, we're going to define the cumulative strain and the cumulative flux. So we're also going to be looking at the flux response now. And by that, I'm going to take the absolute value of the strain or the absolute value of the flux and integrate it over my loading time. And I'm choosing to fix my number of cycles here. You could also fix the loading time instead. And that doesn't really matter at this point, but it does when you start varying the frequency and when you're interpreting those results for that. There's a lot of different ways that you can define things in this system, and I certainly explored many, and it just you have to be careful about what you're interpreting and what you've defined. But so here we fix the number of cycles, and we again for the same applied stress, and this is what we get. So the cumulative strain, as you can see, is really nicely summarizing that increase in strain about the damage point. So we've got 3 different damage locations, and you can see that increase moving with the damage location. Then in dotted grey is the undamaged case. And the cumulative flux, though, is really not showing any difference at all, only a little bit near the boundary for the damage that is closest to the boundary, but it's really quite small compared to the effect that the cumulative strain has. And if we do go back to the full time simulation, then we do see the flux isn't really affected, and that's really because we're applying this stress boundary condition, and the flux is governed by stress gradients here. So it doesn't really get affected by this heterogeneity, whereas the strain, of course, does. We can go one step further and integrate this over space. So here I'm defining the net flux, and I'm moving to an applied displacement this time. So in an applied displacement, it's the flux that's affected rather than the strain, because this time you're imposing your displacement, and so that's tied to the strain, but the stress, however, is the one that's going to change. So at the location of the damage, you're going to get a dip in the stress, which then affects the flux. And so here, the reason I'm defining this net quantity is so that then we have a singular output, and then we can vary our parameters. We can through lots and lots of different values and see how that output changes with these parameters. So here I'm going to show you delta Q, the difference between the damaged net flux and the undamaged net flux. So if it's 0, then the effect of damage, there's no effect of damage on the net flux. If it's positive, then the net flux is increased when it's damaged, and if it's negative, then it's the opposite. So on the left here, I've fixed my frequency at omega equals 10 again, and I'm increasing the damage magnitude, and we can see that the effect of damage increases with damage magnitude as we would expect, so that's good. What we're also seeing is this change of dependence on the location, which I thought was quite interesting. So the effect of damage increases with the damage location up until about d equals 0.5, and then as you can see after d equals 0.5, that relationship reverses and the effect of damage decreases with the location. And then if we vary loading frequency, you're seeing this blow up as you really slow down the loading frequency. And that's mostly because of the way that we've defined our metric with the absolute value, and also the fact that we fixed our number of cycles. So as we slow the loading down, you're increasing the loading time, and so the contributions add up more, and so it blows up. So if you had a different metric where you fixed the loading time and not this number of cycles, then it might not be as big of a difference. And here you have a vanishing porosity, and that's just, I'm not going to get into the details of that, but that is to be expected when you're applying a displacement, a cyclic displacement to a poroelastic material. The model breaks down, basically. Okay, And just to bring this into the context of tendons a little bit, so I mentioned the poroelastic timescale before. If we take some values for the Achilles tendon, and there's quite a few different values that could work, you can get a poroelastic timescale between 59 seconds and order 1,000, which is quite large. And so if we compare this to what our model is saying, then the frequencies 0.5 to 10 are about what the literature says it would be a rehab loading frequency. But what I found interesting was this model can't capture the walking and running regime because you're getting this vanishing porosity. So that's an indication already that maybe either this is the wrong boundary condition, that an applied displacement is not correct, or that the 1D model is not enough. Or the parameters might just be wrong. Okay, and so all of that is, we've got a paper out now on that work, which has recently been published in Soft Matter. And so we go through the effects of the heterogeneous stiffness, also explore heterogeneous permeability and compare the applied stress and the applied displacement. And these metrics, they were quite hard to define, but they can be a really useful tool if you do have data on a tendon to compare against, and then you can infer information like temporal and spatial features using those metrics. Or if you trust your model, you can say, well, I think that the location of the damage is here based on the data from your tendon. And then, of course, this is a simplified model for tendons, but it can be a guide to more complex models, so moving to higher dimensions or introducing a more accurate stress law. And I wanted to highlight as well that this model doesn't just apply to tendons. So other biological tissues, first of all, can be modeled in a very similar way, like cartilage and ligaments, also the brain. But other non-biological systems can also be modeled using this framework. So a lot of other systems undergo this cyclic loading and exhibit heterogeneity. So passing traffic on soil, earthquakes, waves on the seabed, all of these systems can be modeled in this sort of framework. Okay, and now for the last part of my talk, I wanted to talk a little bit about what I'm thinking about at the moment, which is changing the stress law in this model to better capture the tendon mechanics. So I showed you this curve at the beginning of the stress strain law in a tendon. You have this nonlinear relationship, and in particular, you have this toe heel region. And it's sort of agreed upon in the literature that this nonlinear region at the start corresponds to uncrimping of fibrils. So in the tendon, you have these collagen fibrils, which have this wavy structure. They're crimped. And so what's believed is that when they're crimped, the fibrils don't contribute to load bearing. So when you pull on the tendon, the fibrils first need to straighten out, and then once they're straightened out, they start contributing to the load. And so the hypothesis is that this toe region corresponds to the uncrimping of the fibrils. And so there's this paper by Shearer in 2015 who derives a strain energy function based on this this mechanism, this geometry. And to do so, he assumes that the collagen fibrils only contribute to load bearing once they're taut. That the crimp angle theta of r here increases with r, so the most crimped fibrils are at the outer radius and the least crimped are in the middle, which means that when you pull on the tendon, you're getting first the ones in the middle straightening out, and so you get this radius of taut fibrils that increases as you stretch the tendon. And then he assumes that each fibril is individually Hookean and incompressible. So from those assumptions, he's able to write down the Cauchy stress for the fascicle. So the fascicle is the next subunit in the tendon, but we're kind of just going to assume that the fascicle is the tendon. If you want to upscale it, you just sort of need to know the fraction of fascicles within the tendon. So CF here is our fibril fraction. This first part of the equation is just the background matrix. So he assumes that the fascicle is made up of only fibrils and then a background matrix, which is assumed to be neo-Hookean. And so what you're getting is this contribution of the fibrils, which is an integration up to that radius of taut fibrils, or up to 1 once you're past the critical stretch lambda star, where all the fibrils are taut. And then lambda is the fascicle stretch, or I guess the tendon stretch. So how can we use that in our model? This is the Cauchy stress, and we are doing things in Lagrangian variables. So first of all, seeing as we're in a poroelastic material, we've got a compressible material, compressible solid as a whole. We need to consider compressible law. So if we consider that our background matrix is compressible, then our whole Cauchy stress is compressible. So we can convert to a pure stress the compressible solid. And then for our uniaxial deformation, then we just get that the Lagrangian stress is equal to the Cauchy stress. So we can directly use this expression that Shearer provides for our effective stress. So just to compare what those laws look like. So in black here, we've got the neo-Hookean only, and then theta naught is the maximum crimp. So that's there's a crimp distribution basically in this model that I haven't shown you. And you need to provide a maximum crimp angle. So this is for just a few different values of crimp angle. And what you can see really, the most important thing is that the stress law is superlinear compared to the neo-Hookean one, which is a good thing because that means that the tendon is more protected, because when you're applying a larger stress, then it's actually going to be strained less than if it was only neo-Hookean. And you're seeing as well this little sort of toe region at the start. You can see, especially for that theta naught equals 0.25, corresponding to the uncrimping fibrils. And if we look at what that looks like in the poroelastic model, so sort of the same simulations that I was showing you before, but now with this different stress law. And so in black is the only neo-Hookean, and in red is going to be with this uncrimping stress law. This is quite a slow frequency. You're really seeing that the strain is a lot smaller than for the only neo-Hookean stress law. And then the same thing happens if we increase the loading frequency. And then in this last one, if you look carefully at the uncrimping one, so the red line, you're going to see that it takes a bit of time to lift off from the strain equals 0. It's quite fast, but you can, oops, that's the wrong one. You can see it lifting off. And that's the fibril. Obviously, this is in 1D, so it's not capturing all of these fibrils. It basically is essentially one fibril in the end, but it's diffusing down, and so it's sort of uncrimping slowly as it goes down. And so now the question is, well, how do we model damage in this scenario? Well, we can do the same thing that we were doing before and just locally decrease our stiffness. So that, as you might expect, gives us a very similar result, but just with a smaller effect really, because the strain is lower anyway. But it also unlocks other ways to model damage. So we can play around with the crimp angle. So this is the different values of that maximum crimp that I was showing you before. And you're going to get a greater or smaller strain depending on that crimp angle. The variation is quite small, but maybe for a tendon that will be important. And that's sort of how far I've gotten with that so far. But there's a lot of things that we can now, that using this this stress law unlocks to be able to play with within the tendon, and also introducing much more biologically relevant parameters into our model, because they actually correspond to tangible things like the fibril Young's modulus is something that people actually measure rather than this sort of neo-Hookean stiffness in a tendon. What does that mean? Yeah, so to conclude, I got this nonlinear poroelastic framework which captures the bulk mechanics of the tendon. We looked at a completely neo-Hookean stress law and locally decreased the stiffness there and sort of characterized the response. And now we're looking at introducing this uncrimping collagen stress law with a background matrix and exploring how we can model damage there. Something that we're going to look into now as well is breaking a fibril, because that's something that we can quite easily do in that model. And is something that we actually understand what that means. And then other future work is extending this into 2D. It would certainly be more interpretable, especially now that we have this cylinder of fibrils, and working towards integrating more biological parameters into the model. Thank you.
Yeah. Well, thanks for that, Zoe. That was a really great talk.
Thank you.
Does anyone have any questions for Zoe? Yeah, Matilda?
Sorry, I'm figuring out how to... Yeah, okay. Unraise the hand. Sorry. Great work, Zoe. Really super interesting. I just had a couple of questions, if that's okay. One is a proper question on one of the slides where you were talking about the delta Q, so the net flux. I've just been wondering if so are you showing, have I understood correctly, that for higher damage, then you would get a higher flux all over?
So
compared to the undamaged.
In this scenario, yes, but it depends. So, for example, when we look at damaging the permeability, which in our case was locally decreasing the permeability, that decreases the flux, which was also then decreasing the net flux. So it really depends on the scenario. Also, this is absolute flux. So it's, I mean, we took absolute flux because otherwise over a cycle, the flux cancels out. So we're not really going to get any information from that. But that's also going to come into play into interpreting this metric. It was quite a headache to like find these metrics and understand them, I have to say at the start. But in this particular example, yes.
Okay, now I was just wondering because of, you know, if we think of a problem with solid transport to, for example, oxygen or nutrient transport, then would this mean that in principle, obviously in a bit of a forced scenario, you would have higher transport with a locally damaged or locally altered property? That was basically the question, because there are several scenarios where this could even be favorable or looked for in a way. That was
well, what you're getting if you look at like the sort of the snapshot of the flux, you're getting this increase in flux to the left of the damage and this decrease in flux to the right. So you're basically getting like a flux into that damage point. But then also then that sort of changes a little bit throughout the cycle. But that's sort of the most the biggest effect that you're seeing is that sort of profile. Yeah.
Okay, thanks a lot. Yeah. And then if that's okay, just a quick comment if you have it, otherwise, because it's a very, you know, broad topic, but I'm also working on poroelasticity for biological tissues. And one question that I get a lot is, why are you using poroelasticity and, for example, not viscoelasticity? I don't know if you have any, if you can help me figuring out a good answer for the next talks.
I really don't have an answer. I mean, the question that has come up is, oh, should we do poroviscoelasticity? But that sounds awful. So,
Yeah.
but viscoelasticity instead of poroelasticity, I'm not sure. I'm not really well versed in viscoelasticity, so it's difficult for me to know what the viscoelastic model would bring, what it would be, how it would be different, and what it would be capturing differently. I think I like that here you have a clear fluid component and a solid component, which you can sort of at least try and clearly define compared to biological things. And I don't know how that would work in a viscoelastic model.
Thanks a lot. That's great.
Great. Gray, do you have a question?
Yeah, a couple. Just a quick one, really. In sort of normal walking, everyday life, do you know how far out of the sort of heel-toe region we typically operate?
Yeah, we're quite early. So in this small regime, actually, is the walking and maybe even slow running. Yeah, daily activity tends to be quite in that toe heel region.
So in the nonlinear region.
Yeah.
And then the other question I had was trying to get my head around this net flow and even the net strain. I mean, the net flux, as you say, is zero in a cyclic system, but you're sort of rectifying that by taking the modulus. What's the sort of physiological importance of this measure that you're calculating?
That's a great question. I'm not really sure. It kind of came out from trying a lot of different things and seeing how I could characterize the response rather than thinking, how can I relate this to a specific tendon quantity? But that's certainly something that I'm trying to think about more now.
I mean, I suppose I can imagine more with the net strain, in the sense that the damage might get worse. Straining it back and forth and back and forth and back and forth. So you can imagine the tissue weakening over time and having a cumulative effect of that. I was struggling a bit more to sort of picture what this measure of net flux might be useful for.
Just the idea of looking at the flux is also because it seems to be one of the things that cells might respond, not net flux itself, but some kind of flux measure, that cells respond to something to do with the flux, which is why we wanted to look at the flux as well. But going from this net flux to that is definitely quite far off.
Sorry, and this is flux of the fluid component relative to the solid component. That's what you meant.
Yeah.
Okay, thank you. A nice talk.
Thank you.
Great. Does anyone else have any more questions for Zoe? Oliver?
Yeah. Hi. Also, thanks for the nice talk. I guess I had a question kind of related to what Gray was saying at the end there about, you'd imagine that if you've got a slightly damaged tendon and then it's being stretched a lot, that could further damage it. I was wondering if you'd looked at, say, how damage might change throughout the thing, or if it could increase, or if you just always impose there is a damage point, or if that's something you're planning to look at going forwards.
Yeah, that's also another sort of step, but I've been a bit hesitant to just to introduce that on without really knowing how it works, because there's some literature that we know that tendons remodel in response to the mechanical stimulus, but how exactly is a big question, and there's a lot of sort of conflicting literature, and there's not really anything that's really quantitative on that. So it's something that is on my to-do list, that to really scour the literature and see if there's anything that might be able to be translated into at least a phenomenological law to have this like remodeling process. But yeah, that it would be nice to incorporate that.
Cool, thanks.
Brilliant. Are there any more questions for Zoe?
Oh, sorry. Yeah, can I just come back on?
Yeah.
It just occurs to me, you're taking these moduli of, so your net strain, for instance, as sort of integral of the modulus of the strain. And I just wondered, you could get, I think, the same sort of effect if you took the integral of the stress times the strain, which would be, the local work done. And of course, the local work that's been done would accumulate and might more directly suggest increasing damage with time.
Yeah, that's a good point.
And I think it would come out very similarly, because it would essentially then, be proportional to the square of the strain. And then you're really taking the square root of the square of the strain. So I think you get very similar looking results. But maybe a little bit more interpretable.
Yes. Thank you. Good point. I will write that down.
Anyone have any final questions for Zoe? If not, should we all thank Zoe again for a great talk?